All right, we're going to go over our simple harmonic motion review. So let's start with this first one. What is the definition of a simple harmonic oscillator? And what are two examples we studied that we considered to be simple harmonic motion? So, for a simple harmonic oscillator, first thing we're going to say is that the net force always points to equilibrium. That's the first thing that makes it different than regular oscillatory motion. The second thing we're going to say is that the size of the net force increases proportionally as the object moves away from the equilibrium position. Those two things are what make simple harmonic motion simple harmonic motion. Now, the two that we've talked about and the two that we're responsible for knowing are a simple pendulum and a mass on a spring. Those are the two things that we have to know about. Those are the two examples we talked about. So, simple pendulum, the period of a pendulum is 2 pi on the square root of the length of the pendulum and the acceleration due to gravity. The period of a pendulum depends on both length and gravity, but not the mass. So for a period of a pendulum, the mass is completely unimportant. For a mass on a spring, this is a different situation. These are not interchangeable things. The period of a mass on a spring is 2 pi on the square root of m over k, where we have the mass being very important and the spring constant being very important. You change the mass, the period goes up. You change the spring constant, the period goes down. Why are some oscillators, such as a marble, not examples of simple harmonic motion? There are two reasons. One could be no restoring force. I guess the way that we could say that to match this is that the force doesn't point to equilibrium. The other thing that could happen is that the size of the force is not proportional to displacement. For any of those two reasons, that would make it not simple harmonic motion. All right, number 4, we have a simple pendulum, and we're going to calculate some things about it. So for this simple pendulum, we're going to have it hanging straight down. This is going to be my equilibrium position. And to do this problem, we're going to pull it up to a height of 0.2 meters and release it. Now, for the motion, it's going to swing down. It's going to go past equilibrium up to another amplitude, back to equilibrium, and back to its initial position. So, all 4 of those arrows are one full oscillation. All 4 arrows represent one oscillation. So, we'll keep that in mind. Now, as we calculate this period, it's 2 pi on the square root of L over G. Those are the only things that are important for calculating the period of this pendulum. Its length is 0.8 meters and the acceleration due to gravity is 10. We put that in there, the period comes out to be 1.8 seconds. At what time will the mass first reach its maximum velocity? Well, it starts off at rest, and by the time we get to equilibrium, it'll have maximum velocity. And this is something to keep in mind. The maximum velocity is always at equilibrium. Always. So what we're really asking is how long until it gets to equilibrium for the first time? Well, looking at it, that's just 1/4 of my oscillation. So the time to get there is going to be 1/4 of the period. So it's 1.8 divided by 4. Comes out to be about 0.45 seconds. Part C is to calculate the velocity, the maximum velocity of that pendulum bob. So to do that, I'm only going to do it once, but we'll kind of refer to this idea as we go through the review from now on. We're going to make those energy graphs. So at rest, we've got some energy that we're worried about, and at equilibrium, we've got some energy that we're worried about. So since this is a pendulum, our possibilities are gravitational potential energy and kinetic energy. Gravitational potential energy and kinetic energy. At rest, we don't have any kinetic energy because we're not moving. We're up at 1 amplitude and we've got a height, so all of my energy is gravitational potential energy. At equilibrium, we're as low as we can possibly go, so the gravitational potential energy is 0. And at equilibrium, we've got our maximum velocity, so our energy is all kinetic. So in order to find out the maximum velocity of this object, we're going to take the energy at rest, set it equal to the energy at equilibrium. So that's gravitational potential energy is equal to kinetic energy. mgh is equal to 1/2 mv squared. So we see that the masses cross out. And so gh is equal to 1/2 v squared. V comes out to be the square root of 2gh, and so it is the square root of 2 times 10 times 0.2. So that velocity comes out to be, 2 meters per second. We did that over there, so what we're going to do is slide over and say that the maximum velocity of the pendulum bob is 2 meters per second. Now we're going to do part D and look at how the answer to each of the above would change if the mass were doubled. So looking at each one of these things, we'll notice that there's no mass here in our calculation of the period. And when we did energy, since they both depended on mass, the mass doesn't matter for the maximum velocity either, which means for parts A, B, and C, no change. If the mass changes, we experience no change at all. Okay. Question 5, we're going to have a 3 kilogram mass attached to a spring, which is hanging vertically. We're going to pull it down and we're going to release it. First thing, calculate the period. Because this is a mass on the end of a spring, it's 2 pi on the square root of m over k. So it's 2 pi on the square root of the mass, 3 kilograms, divided by k, 100 newtons per meter. We plug that in and the period comes out to be 1.1 seconds. At what time will it reach its first maximum velocity? So if we look at it, we got equilibrium. We're going to start off below equilibrium. And if we do just a quick look at what's going on, we go up to equilibrium, we go past it to another amplitude, back down to equilibrium, and back down to our starting point. And all four of those are one oscillation. So maximum velocity, again, always at equilibrium. That's just 1/4 of my motion. That time is going to be 1/4 of the period, or 1/4 times 1.1 seconds, which comes out to be about 0.275 seconds. That's how long it takes to get to the maximum velocity. To calculate the maximum velocity, it's the exact same thing we did before, but we have spring potential now. So my maximum spring potential energy is going to be equal to my maximum kinetic energy. So 1/2 kx squared is equal to 1/2 mv squared. So the halves go away, and I get kx squared over m square rooted is equal to my velocity. So to get that number, the velocity is 100 times 0.2 squared divided by the mass of 3 kilograms. That velocity comes out to be 1.2 meters per second. Now, what happens to each of these when the mass is doubled? So, looking at the period increases when the mass is doubled. So my initial period is 2 pi and the square root of m over k. My new period is going to be 2 pi on the square root of 2m over k. We're doubling that mass. So the new period is 2 pi on the square root of m over k, that's our original thing, times the square root of 2. Mathematically, these two things are the same. So my new period is my old period times the square root of 2. So A and B both increase by a factor of the square root of 2. Now, part C, we see that the velocity is kx squared over m. That velocity is going to go down. So my initial velocity is the square root of kx squared over m. My new velocity is the square root of kx squared over 2m. That's like saying the square root of kx squared over m times 1 over the square root of 2. So the velocity, part C, gets smaller by a factor of 1 over root 2. More mass, less velocity. More mass, longer period. And this is how that happens. All right, now we're going to get a new period. The oscillation is 4 times per second. So if the oscillation is 4 times per second, the period is 0.25 seconds per oscillation. So to get this new spring constant, I know that the period is 2 pi on the square root of m over k. I've got to solve for k. So we're going to square both sides. Period squared is 4 pi squared m over k. That makes k 4 pi squared m over t squared. So 4 pi squared times 3 over 0.25 squared. All that math gives us 1900 newtons per meter as our spring constant. Okay, number 6. This is where things get fun. Now, we have a collision, and we have a collision happening at a very specific place. So that's going to mean some specific things. So, one thing that means is that the blocks will hit and stick together. That's in the problem. The next thing that's going to happen is that both blocks move after the collision. So the blocks hit and stick together and move after the collision. Here's a fun thing. The velocity after the collision is the maximum velocity of the oscillator. There are a couple of reasons that's true. This is the important part of the problem. One reason that's true is that after the collision, the blocks are at equilibrium. And at equilibrium, the speed is always going to be the maximum velocity. That's just always true for simple harmonic motion. So since a lot of this stuff depends on what happens after the collision, let's do some collision calculations. I know that the initial momentum is going to be the final momentum. Initially, we have the 2 kilogram block moving at 35 meters per second. It's going to hit and stick to the 5 kilogram block, which isn't moving. So afterwards, their velocities added together, we get 7 kilograms times the final velocity. That makes the final velocity 10 meters per second. So, because of this, we know some things for the motion that we're going to need to talk about. First thing, a mass of 7 kilograms is moving in simple harmonic motion with a maximum velocity of 10 meters per second. And this motion started at equilibrium. Very important stuff. This is going to help us immensely with the rest of the questions. At what time after the collision will the two blocks come to rest? So to do that, to figure out when they're going to come to rest, first off, let's look at after the collision how they move. That's going to be my equilibrium position. They're going to start off at equilibrium. They're going to move in one amplitude, stop, turn around, and come back. Move past it, stop, come around, and come back. That's one whole oscillation. And the velocity over here is 0. So they're first going to come to rest in a quarter of a period. That means we need to calculate the period. Period is 2 pi on the square root of m over k. So that period is going to be 2 pi on the square root of 2 kilograms. Wait a minute. We said we had 7 kilograms moving in simple harmonic motion divided by k of 1,000 newtons per meter. When we calculate that, our period comes out to be 0.5 seconds. But that's not what this question was asking. This question wanted to know the time it takes to come to rest. Well, we said that's a quarter of a period, so it's going to be roughly 0.125 seconds. Now, I'm rounding to 0.5 seconds because it's going to make something nicer in a little bit. Part B, what's the maximum compression of the spring? Well, this is our energy problem. We start off with kinetic energy. we end with potential energy. So we start off with kinetic energy. 1/2 mv squared is equal to the potential energy 1/2 kx squared we have at the end. And if we want maximum compression, we're going to solve for x. So x here is the square root of mv squared over k. So that's the square root of 2 kilograms times 10 meters per second squared divided by 1,000 newtons per meter. So the maximum compression comes out to be 0.84 meters. What's the position relative to equilibrium 1 second after the collision? Well, 1 second after the collision is 2 periods. If we've done 2 complete periods, we are back at equilibrium. There you go. What's the maximum acceleration of the 2 blocks? Well, acceleration is the net force over the mass. Our net force here is the spring force. So it's kx over the mass. We're not worried about the negative sign for the spring force equaling negative kx because that's just direction. I want maximum acceleration. I'm not worried too much about the direction. So we've got 1,000 newtons per meter times 0.84 meters divided by the mass of 2 kilograms. Put that all in there, and our maximum acceleration comes out to be 120 meters per second squared. How much energy was lost during the collision? Well, we just did energy, so it's going to be the energy beforehand and the energy afterwards. Energy before the collision, the only thing moving was the 2 kilogram mass, so we're going to look at the 2 kilogram masses kinetic energy. 1/2 times 2 kilograms times 35 meters per second squared. The energy beforehand comes out to be 1,225 joules. The energy afterwards, well, afterwards, both of them are moving, so that's 7 kilograms at 10 meters per second. So the energy afterwards comes out to be 350 joules. So if I'm looking at the energy lost during this collision, start off at 1225, we end up at 350. My change in energy is the difference between those two is 875 joules. All right, the graph below shows the position of a particle which is in simple harmonic motion. I don't know if it's a mass on a spring. I don't know if it is a pendulum swinging. I just know that we're in simple harmonic motion. So the period of motion of this particle, just based on the graph, we need one whole oscillation. One whole oscillation is 4 legs of our trip. Here we happen to start off at equilibrium, but we have to go through the entire range of our motion, not just half of it. So from the graph, one period of motion is 10 seconds. What time will this particle come to rest? Looking at the graph, rest happens when slope is 0. That's when we get rest. Well, my slope is 0 every time we turn around. The first time that happens is 2.5 seconds. Maximum negative velocity. First off, we know that we have max velocity at equilibrium, and if it's negative, we need a negative slope. The first time that happens is right here at 5 seconds. I've got a negative slope, and I'm at equilibrium. At what time will the particle first reach its maximum positive acceleration? Our idea here is that acceleration is always towards equilibrium. So if we look at this motion, when my particle's up here, towards equilibrium is down. Well, that's a negative acceleration. When we're down here, towards equilibrium is up. That's a positive acceleration. The first time we hit that max positive acceleration then is going to be down here at 7.5 seconds. Now, there are some always true rules that would be a good idea to cover here. So, the first one, particle is always at rest at maximum displacement. That's where the particle's turning around. Another thing that's always true, we always have maximum velocity at equilibrium, always true. And we always have maximum acceleration at maximum displacement. The reason that's true, acceleration is net force over the mass. That's kx over the mass. More x, more acceleration. In the case of a spring. We don't know what this is yet, but in the case of a spring, that's true. Broadly applicable. Now, next part of this, at what time does the particle first have its maximum kinetic energy? So we are looking for first maximum velocity. That happens at time equals 0 seconds. That's when we first have our maximum kinetic energy. The next time is at 5 seconds. The next time is at 10 seconds. All right. Now, we get some more information about this particle. It's a mass of 2 kilograms oscillating on the end of an ideal spring. So we need to find the spring constant. Need a little bit of space to do this. So for part F, if we're finding the spring constant, we know the period is 2 pi on the square root of the mass of the object divided by the spring constant. We got to square both sides. We got 4 pi squared m over k. So k is 4 pi squared m over the period. And for what we have going on here, that's 4 pi squared times the mass of 2 kilograms divided by the period squared, which, based on the graph above, is 10 squared. When we calculate it out, that makes K 0.8 newtons per meter. So the spring constant is 0.8 newtons per meter. The magnitude of the maximum velocity, we've done this before, but this is just an energy problem now. So the maximum potential energy, 1/2 kx squared, is equal to the maximum velocity, the maximum kinetic energy, 1/2 mv squared. Halves go away, and the velocity is the square root of mv squared, the square root of kx squared over m. So it's the square root of 0.8 times 3 meters as our maximum displacement squared over the mass of 2 kilograms. We get 3 meters, and I know this was hard to see. This is 0 and this is 2, and that has to be 1, and so that makes that 3. So my maximum displacement is 3 meters. That makes my maximum velocity 1.9 meters per second. So the magnitude of the maximum acceleration. Acceleration is net force divided by mass, so that's kx divided by the mass. So that's 0.8 newtons per meter times my maximum displacement of 3 meters divided by the mass of 2 kilograms, giving me a maximum acceleration of 1.2 meters per second squared. Graph the potential energy. Well, we've got one more always. We always have maximum potential energy at maximum displacement for all simple harmonic motion, but especially for a spring. If we look at a spring, the spring potential is 1/2 kx squared. So when x is big, potential energy is big as it's going to get. So it's 1/2 times 0.8 times 3 squared. That's my maximum potential energy. So for this problem, that comes out to be 3.6 joules. But it's always at maximum displacement. And another always, we always have zero potential energy at equilibrium. So every time we're at equilibrium, if we look at the graph above, we end up with zero potential energy. Every time we're at 3 meters or negative 3 meters, because we're squaring it, doesn't really matter, we end up with our maximum potential energy. So every time we're at 3 meters or negative 3 meters, we have maximum potential energy. So our graph of potential energy as function time looks like this. Hopefully your graphs look a little bit better than mine. All right, that's our review. Now, there's one thing we didn't cover on this because we did it in the lab, so there's some things I want to point out about the lab that are important to remember. Well, there's the lab, and then there was that graphing worksheet we did right after that. So, on the pendulum lab, we looked at what affected the pendulum. We linearized a graph. And we used the slope and we need to be able to use the slope to find L or G or K or M. We did that with the lab and we did that with the worksheet right after the lab. Okay, that's what we've got for the review. Good luck on your test tomorrow, and thank you for watching.